Right, let me show you how to answer the June 2020 Paper 2 Foundation exam. It's physics and it's worth 60 marks. I'll do a walkthrough explaining all the science. Question 1, A. Figure 1 shows the insides of a mains plug. The mains plug has 3 safety features. One of these safety features has been ticked in the table. Put 2 more ticks in the table to show the other 2 safety features. Right, the earth wire is for safety and the fuse wire is also for safety. The earth is needed if the appliance has got a metal case to stop it from becoming live, and the fuse is needed to stop too much current going into the appliance. The meter on the battery charger shows the current supplied to the battery. The meter on the battery charger is, right, well, if it's showing the current, it must be an ammeter. Part 2. The battery charger supplies a steady current of 2.5 amps. So that's our current, I. Calculate the charge flowing, so Q, that's our target, to the battery in 8 minutes. So that's our time. Now remember, you've got to convert minutes into seconds. So to get the charge, you just do the current, which was 2.5 amps. Multiply that by the time, so that's 8 minutes times by 60 seconds per minute. And that comes out as 1,200. And that's coulombs if it's charge. Question C. The transformer in another battery charger has a primary coil and a secondary coil. The voltage across the primary coil is 230 volts. The voltage across the secondary is 15. The current in the secondary is 3.1 amps. Calculate the current in the primary coil. Right, the current in the primary coil. So they've already rearranged the equation for us. So we just need to pop the numbers in. So the secondary voltage was 15. We need to multiply that by the secondary current. So the secondary current was 3.1 amps, and we need to divide that by the primary voltage. So the voltage in the primary was 230. And when you pop that in your calculator, that comes out as 0.2022. And that's current, so it's amps. How many decimal places? Right, they have just done that to 1 decimal place, so we'll just do hours to 1 decimal place, so 0.2. I'd still leave the long number in here though, so that's fine. And then short number down there. Question 2. Figure 3 shows a toy used to launch a ball. Right, so grab the handle, pull that down, and then it'll whack the ball up when you release it. One end of the spring is fixed to the handle. One end of the spring is fixed to the handle. The other end of the spring is fixed to the support. A child pulls the handle, stretching the spring. Figure 4 shows the toy with the spring stretched. Which of these shows the forces acting on the handle when the child keeps the spring stretched? Right, well, if they're keeping it stretched, they are basically pulling the handle one way and the spring will be trying to pull the handle back the other way. If they are keeping it stretched, it'll be still, so that means that the forces will be equal in size but opposite in direction. So the answer is D. Part 2. In figure 4, the extension of the spring is 0.070. So extension that's X. The spring constant K is 20. Calculate the force, so that's our target force F, to extend the spring. Use the equation, right? So it's already got the equation in the right form for us. It's force equals something or other. So there we go. We're happy with that. Just need to bang the numbers in. So K was 20. So that's 20 newtons per metre. And we need to multiply that by the extension, which is 0.07 metres. Right. That's in metres and that's in metres. So those units are fine. You don't need to convert anything. If it gave the extension in centimetres, you'd have to convert that into metres. Just be careful. And when you do that, it comes out as 1.4. And that's newtons. Part B. The child pulls the handle until the pad is against the support as shown in figure 5. The extension of the spring is 0.09 metres. So that's extension X. The spring constant K is 20. Calculate the work done. Right, so they've already rearranged the equations for us, so we don't need to do anything with it, except for just put the numbers in. Right, so extending the spring by 0.09 metres, so that was our extension. So if we just do a half, so that's 0.5 times by K, so that's 20 newtons per metre, and then multiply that by the extension. So the extension is already in the correct units, and we need to square it. All right, make sure you remember to square it. That's where the students make a lot of mistakes, and that comes out as 0.081, and that'll be joules because it's work done, which is the same as energy. Now they've gave it to 2 decimal places, so if we just give ours to 2 decimal places, 0.08. But once again, I always write the full number up here when I do the main calculation, and then if I want to simplify it, I put the simplified version down in the actual place they want it. Part 2. The child lets go of the handle. The ball starts to move. The spring returns to its original length. Describe the energy transfer that takes place when the ball starts to move. Right, so you've got elastic energy in the spring. Elastic potential energy. In the spring. And that's going to get transferred into kinetic energy of the ball. Or kinetic energy in the handle, it's up to you. Part 3. The child can only stretch the spring until the pad is pressing against the support. Explain how the design of the toy prevents the spring from becoming damaged. So the pad is pressing against the support. Let's have a look at that. Yeah, right. If this little pad wasn't here, then you'd probably just be able to keep on pulling that spring back, and it would just get stretched beyond the elastic limit, and it would permanently stretch the spring and break it. So the spring can't stretch beyond its elastic limit. So no permanent extension. That could get you 3 marks, so we'll definitely get the 2. Question 3. Figure 6 shows a part of a machine used to separate steel cans from aluminium cans. Right, the cans are carried along a moving belt. The belt goes around a roller. The roller is a magnet. Each can falls into one of the containers. Explain how this machine separates the steel cans from the aluminium cans. Right, so the cans come along here. This roller is a magnet. Now you can see that some of the cans are still attached to the roller because they must be magnetic, and they fall into container A, whereas any cans that are not magnetic just fall off the end into container B. So basically steel is magnetic, they're going to end up in container A, and aluminium is non-magnetic, so they're just going to fall off the end into container B. So it's only worth 2 marks. We'll definitely get 2 because we've said 4 things. You'll probably get 2 marks just for talking about the steel or just for talking about the aluminium. I've said both just to be safe. Question B. A student investigates magnetism using 2 toys as shown in figure 7. Rubber band on a toy brick, haha. Hey, go and play with that, son. Here's your Christmas present. Right, the other one's a toy car. Right, they've both got magnets on. There's a magnet attached to the top of each toy. The student moves the toy brick towards the toy car. Right. The magnet on the toy brick repels the magnet on the toy car. On figure 7, label the North Pole and the South Pole on the magnet attached to the toy brick. Right, well, if it repels when this comes close, if that's north, then that must be a north as well, because like poles repel. And if it's north on that end, it must be South Pole on that end. Part 2. Explain why the toy car starts to move only when the toy brick gets near to the toy car. Right, so as you get close to the magnet, you get a strong magnetic field, and as you get further away, the magnetic field's weaker. So the car only starts to move when this starts to get closer. So the strength of the magnetic field depends on the distance from the magnet. Part 3. The student thinks that 2 magnets on top of each other will produce a magnetic field that is stronger than the magnetic field from a single magnet. The student has a meter ruler and more magnets available. Describe how the student could develop this theory, this investigation, a testes theory. Right, so what you want to do is first of all do what they've done. Just have 1 magnet. Put your ruler down here. Now see how close you can get that magnet before this magnet starts to move away, and then measure that distance. Then what you want to do is pop another magnet on the top here and repeat the experiment. See how close you can get this magnet now before that one starts moving away. Measure the distance when this car first starts to move, and then compare the distance when you had 2 magnets to the distance when you had 1 magnet. Now this person thinks that 2 magnets is stronger. Well, if that's the case, then that car will start to move away when this distance is bigger, when you've got two magnets. Now, how do we write that? I'll show you. Well, let's draw a little picture first. So there's the brick. There's the magnet. And there's your ruler. And then there's your toy car. So use one magnet on the brick. Move the brick towards the car. Place a ruler between the brick and the car. Measure when the car starts to move. Then repeat with two magnets. So I'll pop another magnet on the top there, north and south. Repeat using two magnets on the brick. Measure the distance when car moves. Compare the distances. If two magnets were stronger, the car will start to move when the brick is further away. Greater distance. Well, you could get 6 marks for that, so if it comes up as a 6 marker, happy days. Question 4. A student investigates resistors connected in series in an electrical circuit. The student has a 3-volt battery, a 22 ohm resistor and a resistor marked X, as shown in the picture. The student does not know the value of the resistor marked X. The student decides to measure the potential difference, which is just the voltage, across resistor X. Figure 8 shows the circuit that the student connected. The circuit's connected incorrectly. Describe how the student should correct the mistake. Right, well, it says it here. The student decides to measure the potential difference of voltage across resistor X. So basically that voltmeter needs to be moved across resistor X. So I don't know why they've put it over there. That's crackers. So move the voltmeter parallel with resistor X. Part B. The student corrects the mistake. The voltage across resistor X is 2.1 volts. The circuit is connected to a 3-volt battery. State the value of the voltage across the 22 ohm resistor. Right, so that's X is 2.1. Let's go back and have a look at the picture. So if X has got 2.1 volts, and we know that 3 volts is going in total, that means that when you add all of that together, it should equal 3 volts. So basically this, however many volts this has, it'll be 3 volts take away the 2.1 volts. So that equals 0.9 volts. Because remember, when they're in series, this voltage plus this voltage has to equal the voltage that went in. Part 2. The current in resistor X is 0.041 amps, so that's current I. The voltage across resistor X is 2.1 volts, so that's V. Show that the resistance must be about 50 ohms. So resistance is question mark. That's what we're trying to work out. Now, we need to rearrange the equation to get resistance then, don't we? So if we do the magic triangle, do a divide by sign and do a multiply by sign. So I times by R, so we can pop that in there. I times by R, and then one thing in one space. So shove that thing in the space, so V goes on the top. Now cover up what you're looking for. We're looking for R. What we're left with? V divided by I. So R equals V divided by I. So if we just pop the numbers in, it's a common mistake. People will probably just do 2.1 times by 0.041 because they'll just go off that equation without rearranging it. So that's a mistake that students commonly make. Right, so the voltage was 2.1 volts, divide that by the 0.041 amps, and that comes out as 51.2 ohms. And that's what they've said. They said show that the answer was about 50, and it is, it's 51.2. So you knew that your answer was going to come out as round about 50. So if it didn't, you know that you've done something wrong. Part 3. Calculate the power. So power is our question mark. In resistor X, when the voltage across X is 2.1, so that's V, 2.1, and the current in resistor X is 0.041. So that's our current. Now, you have to learn the equations. So power equals current times by voltage. P equals I times by V. Okay, so we'll just pop the numbers in. So the current was 0.041 amps. And voltage was 2.1. And that comes out as 0.0861 watts. How many decimal places shall I do it to? Well, what's the most Dave gave it? To 1, 2, 3. So we'll do ours to 1, 2, 3. So it's 0.086. Part 4. Calculate the overall resistance of the 22 ohm resistor and resistor X. Right, so where was it? Resistor X came out as 51.2, so we'll just say 51, and the other resistor was 22. 22 plus 51. So that equals 73 ohms. Part 5. The current in the circuit is 0.041 amps. The voltage across the battery is 3 volts. Calculate the energy transferred in 2 minutes. So energy is our target. 2 minutes, that's time. Remember, that needs to be converted into seconds. Right, so we're trying to work out the energy, and the formula they've gave us already lets us work out the energy, so we don't need to rearrange it. Just pop the numbers in. So the current was 0.041 amps. Multiply that by the voltage, which was just 3 volts. And then multiply that by the time, so that's 2 times by 60. So they have tried to catch us out a little bit there. That's a bit cheeky, but they will do that to us, don't worry. And that comes out as 14.76. And that'll be joules, as it says down there. How many decimal places have they done? 1, 2, 3. That's the most, so we'll just leave it to the 2. That's fine. 14.76. Question 5a. Figure 9 shows a small piece of copper about 3 centimetres high. The student wants to determine the density of copper. The student uses a balance to measure the mass of the piece of copper. Explain how the student could measure the volume of the piece of copper. Right, now if that's 3 centimetres, that's quite big. There's 2 different ways of doing it. You either pop it into a measuring cylinder, fill that up a little bit with water, and then you'd pop that in. And then the water would go up. And if that's volume 1 and that's volume 2, then the difference between those volumes would be the volume of the copper. However, I think the better way of doing it would be to use a displacement canister. So if you've said that, you still get the marks. But because this is quite big, I would personally be tempted to use a displacement canister. Now what you do is you fill it up to the spout with water. Put your measuring cylinder over here, empty. And then you would pop your bit of metal or whatever the object is into the displacement canister. Now the water would start to spill out. So you'll get little drips of water coming down here, and it would all get collected into this measuring cylinder. And whatever that volume is, that's the volume of the object. So I'll show you how to write that. Catch the displaced water in a measuring cylinder, and displaced water equals volume of copper. So I don't know, you might prefer to see it that way, you might think it's easier. It's up to you, you'll get the marks whichever way you see it. Part 2. The mass of the piece of copper is 0.058 kilograms. The volume of the piece of copper is 6.5 times 10 to the minus 6 metres cubed. Calculate the density of the copper. So that's like a wiggly P for density. So to get the density, you've got to do the mass divided by the volume. So pop the numbers in. And that equals 8,923. And that was kilograms divided by meters cubed. Question B. The student wants to determine the specific heat capacity of copper. Figure 10 shows a piece of copper with a thread tied around it in a glass beaker of boiling water. The student leaves the piece of copper in the boiling water so that the copper reaches a temperature of 100 degrees C. So they've boiled the water, so that goes to 100 degrees C, and because the copper's in there, the copper also goes to 100 degrees C. The student uses the thread to take the piece of copper out of the boiling water. The student puts the hot piece of copper into a different beaker of cold water, and that's at 20 degrees C. The apparatus is shown in figure 11. Right, so they've picked this copper out using the thread and they've plopped it into this water. So this water here was 20 degrees C. Okay, and remember that copper was 100 degrees C. So basically the copper is going to get colder and the water is going to get hotter. The student assumes that the thermal energy gained by the water equals the thermal energy lost by the copper. The water and copper both reach a temperature of 22 degrees C. So as I said, the copper got colder and the water got hotter, and they've both ended up at 22 degrees C. The cold water gains 1050 joules of energy. So remember, that equals the energy lost by the copper. Okay, so the thermal energy gained by the water equals the thermal energy lost by the copper. It's quite wordy, this question. That's why it's always important to try the questions before you go into the exam. So, you know, if it's something similar, you know what's going on. The mass of the piece of copper is 0.058 kilograms. So that's our mass of copper. Part 1. Calculate a value for the specific heat capacity of copper using these results and use the equation change in thermal energy equals mass times by specific heat capacity times by change in temperature. Are they kidding? Only 2 marks for this. Are they having a laugh? So they haven't even rearranged the equation for us, alright? So we're trying to work out the specific heat capacity of copper, which is this value C. So the first thing we're going to have to do is rearrange the equation. Now, make sure you do a nice wide magic triangle this time. Do a top shelf, and this time we need to have 2 multiplied signs on the bottom. Alright, because we've got 1, 2, 3, there's 4 things. Okay, normally in a magic triangle you only put 3 things. Right, we've got room for something times by something times by something. And this is it here. M times by C times by delta theta. So shove that in. M times by C times by delta theta. So delta means change in, and theta is the temperature. Change in temperature. Change in temperature. And the delta Q, remember delta means change in, and Q is thermal energy. So delta Q must go on the top. Now, cover up what you're looking for. We're looking for C, and what are we left with? So C, the specific heat capacity of copper is going to equal delta Q on the top divided by mass and then times by the delta theta. So mass times by delta theta. Okay, and this needs to be the heat of the copper, and this needs to be the temperature of the copper, and that needs to be the mass of the copper. Okay, everything's to do with the copper. Right, so how much heat energy did the copper change by? It was 1050. Now technically that's how much it's lost. So 1050 joules. Now technically that should be a minus because we've lost it. Now what's the mass of the copper? 0.058 kilograms was the mass of the copper. And we need to multiply that by the temperature change of the copper. Now remember, it went from 100 and it ended up down at 22. So 100 take away 22. Now that's 78. But remember, technically that's minus 78. Okay? Because it's lost that temperature. Anyway, look, if you forget about that minus and you forget about that minus, they'd cancel out anyway, so don't even worry about it. But if you have understood what I've said, then great. And this equals 232. And that's joules per kilogram per degree C. Can't believe you've got to do all of that to get 2 marks, mind you. Ridiculous. Part 2. The value for the specific heat capacity of copper obtained from the student's results is lower than the correct value. So the student's results was like 232. Maybe the correct value was like 250. State 2 ways that the experiment could be improved to give a value that is closer to the correct value. So remember, to get our value of C, we had to do the change in the energy divided by the mass times by the change in the temperature. So basically our value is too small. So this here might have been too small then. So the amount of heat energy. So instead of the heat energy going into the water, we might have lost the heat energy. So how do you stop the heat energy being lost? Well, look at this. They haven't got any insulation on and they haven't got any lid on. Plus, some of the energy from that copper probably went into the glass rather than just staying in the water. And some of the energy from the copper would have been lost when they were trying to get it out of that water and put it into this water. So maybe they need to do that a little bit faster as well. So that's what I would say. Insulate the beaker. Transfer the copper faster. And this will reduce heat loss to the air. So we don't want the heat to be lost to the air, we want it all to go into the water. Question C. A long piece of wire is made into a coil as shown in figure 12. The coil is connected to a low voltage power supply. Describe how this coil could be used instead of the Bunsen burner in figure 10. Well, the Bunsen burner heat the water. All that we're going to do is use this to heat the water instead. So what is it? Well, it's just a heater. So we just need to put an electric current into it and then pop it into the water. Put the coil in the water and turn on electric current. The coil will heat the water. I mean, that's basically an electric heater. You know? Question 6. Figure 13 shows a drone. The drone has 4 spinning blades. The upward force produced enables the drone to rise in the air. The speed at which the blades spin is measured in turns per minute. Figure 14 shows how the upward force produced by the 4 blades depends on the speed at which the blades spin. Describe the relationship between upward force and the speed shown by this graph. Right, so this is the speeds in turns per minute. So 2,000, 4,000 turns per minute, 6,000 turns per minute, 8,000. So the speed of turns per minute is increasing, and you can see the upward force is also increasing. But because it's a curve, we say it's non-linear. So upward force increases as speed increases. And it's non-linear. If it was a straight line, say it was linear. Part B. A different drone has a mass of 4.5 kilograms, so that's our mass. This drone rises from the ground to a height of 20 meters. So from the ground, so that's nothing, up to 20. So the change in the height equals 20 meters. Calculate the change in gravitational potential energy So the change in GPE, that's our target, when the drone rises through the height of 20 metres. And it tells us that gravitational field strength on Earth's 10 newtons for every kilogram. Right, you're going to need to memorise this. So the change in the gravitational potential energy equals the mass of the object times by the gravity of the planet times by the change in the height. So pop the numbers in. The mass was 4.5, gravity was 10 newtons per kilogram, and the change in the height was 20 metres. And when you pop that in your calculator, it comes out as 900. And all energy is measured in joules. Part 2. State the amount of useful work done by the blades as the drone rises through 20 metres. Now the thing is, that drone is now in the air and it's got 900 joules of energy. So as it drops, it would release the 900 joules of energy. So basically the 900 joules of energy is useful because it can release it as it falls. So the answer is just 900. Now what you'll notice, it's only worth 1 mark and there's not any room really to do a calculation. So these questions come up all the time. Whatever this answer was here, you just use the same answer for the next question. That's quite common, that. So just watch out for that. There's a tip. Part 3. It takes 4 seconds, so that's the time, for the drone to rise through the 20 metres. Calculate the useful power, so power's our target, developed by the blades in this time. So do you know that the equation for power is the energy transferred divided by the time it took to transfer that energy? Right? If you can transfer lots of energy in a short time, that means you're powerful. So let's see how powerful this thing was. So it transferred 900 joules of energy and it did that in 4 seconds. So that comes out as 225, either joules per second or power is measured in watts. So 225. And finally, our 6 marker. Question C. The blades on the drone are turned by electric motors. The electric motors are powered by a battery. Figure 15 represents the energy transfers involved when the drone rises from the ground. Right, so you've got the battery loses a little bit of energy but transfers the rest of the energy to the motors. Right, what type of energy is in a battery? Well, it's chemical, isn't it? Because if a battery splits on you, it puts acid all over you, and it's acid's a chemical. Right, the motors, what's that powered by? Well, they'll be electric. And if it's a motor, it's spinning, so that's going to kinetic energy. The blades are spinning, so that's kinetic energy. That's lost a little bit of energy. That's lost a little bit of energy. What does it lose energy as? Well, it always loses energy as heat. Probably sound as well. You know what I mean? When these blades are spinning, they're quite noisy, aren't they? Describe the changes in the way energy is stored when the drone rises from the ground. Your answer should refer to the energy transfers. Right, so you've got chemical energy in the battery, gets transferred into electrical energy in the motor, plus some energy is wasted as heat to the surroundings. Right, then electric energy in motor gets transferred into kinetic energy in motor, and the blades, because the motor will spin and the blades will spin, more heat energy gets wasted, plus sound, more heat energy plus sound gets wasted. And if the drone's above the ground, drone gains gravitational potential energy, GPE. 1, 2, 3, 4, 5, 6, 7. Right, that's it. We've easily got our 6 marks. And that's the end of that paper. So it's not just the answers. Remember, when I do these walkthroughs, it's teaching you all the background science as well. And I'm telling you, you can improve your grades massively by going over as many past papers as you can. So make sure you binge me past paper playlist. And listen, good luck with your exams. Okie dokie. Work hard, be nice, and bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.